This conference will now be recorded.
Hello, everyone. This is Brian Gockel, Weather Service Office of Observations, and we're here for the weekly Satellite Book Club. Our presenter this week will be Randy Bowers, and Chad Gravel is here to facilitate the discussion. Today's topic is the examples of mesoscale analysis in winter weather using GOES imagery. You probably heard the prompt that the session is being recorded. And we'll follow the usual agenda with Q&A after the presentation. And participants are encouraged to post your questions in the chat room, and Chad and Randy will facilitate them through and respond to them through there. We are always looking for presenters for our upcoming briefs. We have some scheduled for the next few weeks, but always looking for future presenters. So if you have a topic you're interested in, please contact the Tower-S team, and Brian Mata of the training team can help if you have any questions related to the development of training materials. Thanks in advance for today for the preparation the Tower-S team has done to bring this Satellite Book Club together. Thanks, Kashad, for getting me prepped here in Jordan's absence. Jordan has a conflict today, can't make it. Also, thanks to the OCLO, GOES-R, and JPSS programs, and all of you participants for your continued support and interest. I'd like to introduce Randy now. Randy has over 8 years experience forecasting at several different NWS offices on the plains, and currently is a meteorologist at WFO Norman. Meso-analysis is one of his passions, and the challenge of finding subtle details in observational data that explain the behavior of the atmosphere and allow us to more accurately communicate what will happen to with our core partners. That's an aspect he enjoys most about his job. So welcome, Randy. Just a sound check that makes sure that we can hear each other and everyone can hear us.
Okay, sounds good. Thanks, Brian. Can you hear me okay?
Sure can. Take her away. Thank you.
All right, sounds good. Thanks to you, and thanks to the entire Tower-S team. I've always thought it's an excellent format to sort of share these topics and discuss them. So really appreciate the opportunity to be able to talk about this one event. Now, we've been very active in Oklahoma from a winter weather perspective this year so far. So I've got a loop up here. Now, it depends on my connection and your connection on your end, but I think you should be able to get at least some of the images come through here. It's a very quick loop, so sometimes it doesn't come across very well, but at least it should give you kind of a broad picture of what we dealt with on this day. This was back on December 2nd. And so on December 2nd, we had kind of a scenario where we had a localized area of very, very heavy amounts in northwest Oklahoma. And we ended up with locally up to about 15 inches around Buffalo, Oklahoma. So it's really impressive event that you can kind of see. A little bit of background noise there, but anyway, you can kind of see on this radar loop here that it was kind of a classic storm system, the way things evolved in sort of a classic sense with a kind of a deformation band towards the end. But we'll get into the details of that here in a little bit and talk a little bit about how meso-analysis really proved to be very important with this particular event. But here's the kind of the snowfall totals of what we had. And we ended up, again, a kind of a local area. We thought early on that we may be sort of involved in all of northern Oklahoma from I-40 northward, but as time passed and we really started to analyze the thermal profile, it became clear that it was just kind of more of a confined area in northwest Oklahoma that would see the really heavy rates. And I feel like the forecast went really well leading up to it for sure, but being able to kind of take it that extra mile and provide that detail from mesoscale analysis ended up being pretty important for our core partners as well. So we'll talk a little bit about that going forward. So, rooted in sort of the broader scale or the synoptic scale, I think it's always important just to touch on this and really to talk about mesoscale analysis to first start with the synoptic scale and talk about how that's important to at least get the forecaster's frame of mind right, to know what the level of expectations are, and so they kind of know a spectrum of what may be possible is pretty important. So, there's been some previous work in our office by a now retired lead forecaster that identified 6 patterns that I think is important, and we've been really kind of looking at that the last few years and kind of updating that a little bit. But one of our most common patterns of the synoptic pattern that brings heavy snow to Oklahoma ends up being this type D pattern, this migratory eastward moving closed low, and this is exactly what we had in this case. But what was interesting about these early findings that the forecaster did many years ago was that found that, and this is the case in most locations, but here in Oklahoma, the cases that they looked at for heavy snow of 4 inches or greater ended up almost always being associated with mesoscale phenomena. So it's really important to say, okay, you've got this broad scale synoptic pattern, but now we can take this down to the mesoscale, or we know that we may have these mesoscale features that are associated with that. So it's just a way to kind of get the forecaster's mind set where it needs to be to anticipate what may possibly happen with that. So, and when we updated this, Phil Ware and I and a couple other people in the office kind of looked at that previous work, and then we wanted to kind of see how that fell as far as using the North American reanalysis and looking at 700 millibar heights, because we figure, well, if this is a mesoscale process going on in most of these cases, then it's probably tied to, you could probably see some signal in the mid-level closed low, the 700 millibar pattern. And indeed we did. Of the 53 cases that we looked at, 41 had a very well-defined closed mid-level low that was anomalous, had negative height anomalies associated with it. So, and the others were just the patterns that fit more of an open wave and a kind of a transient band of heavier snow amounts. But in the majority of cases, we did have sort of a closed low that was involved with the situation that brought the mesoscale banding on the north and northwest side of it. So it's a pattern we know to look for. Most forecasters know that's kind of winter weather forecasting 101, but it's just important to kind of calibrate our mindset to know that's what we look for when we really start to dive into the details for mesoscale banding and potentially rates that may exceed what our forecast has. We know those gradients can be very tight, and that's kind of the first step in identifying that and being able to clarify. So, and then we're all familiar with this kind of the airstreams and how things work with these mid-latitude cyclones. The warm conveyor belt typically has the left branch that will wrap back around the closed low, and that trowel region on the north side of the closed low that kind of culminates in the end of it to the western, the downstream end, that ends up being kind of where some of the heavier snowfall rates end up being that deformation band. So this is pretty common, we know this, but one thing as far as mesoscale detail, really diving in the details where satellite can really help is pinning down exactly where that dry slot ends up being. The dry conveyor belt, sometimes that gradient's really tight, and then we lose moisture in the mid-levels and we don't have the dendritic growth, and then at best sometimes all we have is low-level saturation and maybe some freezing drizzle on the back end. But that's kind of a make or break scenario, as we all know. Anybody that's been involved in winter weather forecasting, the exact position of that dry slot on the back end is very important. So kind of watching the trends throughout the day and being able to say, okay, well, here's where the dry slot position is, and we can extrapolate that out a few hours and start to maybe trend the forecast up or down or tighten those gradients of snow amounts and that sort of thing. Very, very important in the kind of that meso-analysis process. So we took this storm and just took a simple screenshot of water vapor image. This isn't a loop or anything, but just to try to trace out some of the airstreams. And this is just a rough approximation here, but you can see pretty clearly where the convection is along sort of the Sabine River area there, the border between Louisiana and Texas, being within the warm conveyor belt through Texarkana region and then eastern Oklahoma, and then curving back in, wrapping back into the closed low across western Oklahoma, where the trowel becomes much more defined. You'll see that in some of the loops going forward, how well defined this trowel was. And I want to emphasize this case was really pretty straightforward. Again, the forecast worked out pretty well. It's just understanding kind of the thermal profile aspects and where specifically the precipitation type transition would be, and then kind of refining those gradients as we got into the near term. That was kind of the challenge for this event. One thing I've always found interesting, and there's some material out there on this, it may not be in wide use now. Some people that are on the call may use this or may be familiar with it, but I found some pretty good use of this. Is if you're going to find model errors, if you're going to kind of look upstream and see where there may be some model errors, one of the most effective ways to do that is to take the potential vorticity pressure fields of the model and just overlay that on upper level water vapor. And then sometimes you'll see these mismatches where things kind of just don't quite line up. You may see in south central Oklahoma in this case now this case was pretty well represented. There were no major errors or anything, but there might have been some indication where the dry conveyor belt may have extended a little further south into south central Oklahoma, or there may have been just a little bit of a timing issue with some of this back upstream. Now, models are so good now and they're so in tune with, some of the satellite information and all that gets integrated in that for most part, this isn't a major issue. But sometimes these smaller scale short waves, you can pick out little differences in timing and maybe magnitude that you can extrapolate downstream and say, well, given what the model PV pressure field show relative to the water vapor gradients, maybe we need to think about adjusting the timing just a little bit. So it's one area where it's I think that the skilled analyst of water vapor can do some good to sort of identify some of those. But they're frequent, they're few and far in between these errors that you see in the models. But that is one area where, again, satellite can be very useful. All right, so here's the good stuff. Here's the water vapor loop. You'll notice a lot of dry air that's kind of getting wrapped in this early on, but then we start to moisten up pretty good. And then you see a pretty well-defined warm conveyor belt that wraps back around the closed low and then back into the deformation band on the panhandles of Oklahoma and Texas. But you'll notice as the loop goes through that there is some enhancements and moisture in the water vapor fields, kind of in that mid-morning time frame, right about here in the next few images. You'll see when it kind of, you see that enhancement there, and it really shows up in IR satellite, which we'll show later on. But that, we tied that with some of the heavier snowfall rates, and we're able to kind of communicate that to our partners, saying, hey, the satellite imagery suggests that we may really be increasing the rates, the snowfall rates across a small area. So that was one key use of satellite. Now, what was really interesting in this case was that in Northwest Oklahoma, we don't have the best radar coverage. Now, up around Buffalo and the state line, it's not too bad, especially if you use Dodge City radar. It's not, the beam's not too high, it's not spread too wide, so you can usually get pretty good, kind of from a thunderstorm warning aspect, we do pretty well with that. But then you get any further south, you get down into Ellis County and closer to the bottom part of this image here around Arnett, Oklahoma, and it's a little tricky, especially with some beam blockage that occurs from the Vance Air Force Base radar, which you see here in this image. So yeah, there's a pretty well-defined snow band there, but it's not as well-defined as maybe we would like, or maybe we would see if it were in closer proximity to the radar, that's for sure. But especially down on the southern end, closer to Arnett, is a little bit difficult to see with some of the beam blocking. So this was a little bit of a challenging case to fully resolve and to fully see the progression and the movement and sort of the placement of the mesoscale snow band in this case. So it's there, but it's just not quite as clear as it could be, or that we would hope for it to be. We can use some of the tricks like on dual pole, the KDP values. If you go a little higher up in the radar, in this case 1.3 on that image to the right, you'll see some of the enhanced KDP values, which I think Joey Pica and a few others have done some research on that sort of correlate to really good dendritic growth in the dendritic growth zone. So you get a lot of dendrites, and then so that can really drive your rates up quite a bit. The color scale that's default in AWIPS sometimes isn't the best for seeing that. You really can't pick it out too well. So that's something to be aware of. In this case, you can see it's minor enhancements that you see in the KDP values is all it takes to really signal to you that, hey, we got a lot of dendrite growth going on in that critical temperature layer up in the mid part of the atmosphere. So that was one thing that we can use on the radar perspective. But you just can't replace in those types of scenarios satellite, and really just taking that information in and saying, okay, well, suddenly we have these convective elements that really blossom in this area. So that really drives our confidence up that we're dealing with some pretty heavy rates across, say, Harper and Ellis County and far northwest Oklahoma here. So you see this loop that moves through, and we kind of got it to where it slows down just a little bit so you can really see the detail during that critical time frame of mid-morning when we were picking up some pretty impressive rates in northwest Oklahoma. So I'll let that loop through one more time. You can see early on, not a whole lot, but then suddenly we start seeing these convective elements that really blossom in northwest Oklahoma. And we were able to kind of express to our,
Yeah, Randy, this is Chad. So when you guys saw these convective elements, was there any lightning associated with them shortly afterwards?
We didn't notice any. We looked in GLM and cloud to ground, cloud to cloud, and did not see any, as far as I know. Now, the challenge with this event is we were some of the meso-analysis was being done through telework, and we were doing the best we could from home. But as far as I know, in communication with the office, I don't think we had, it was just one of those scenarios. It was just enough convection, but maybe not enough charge separation to get much lightning out of it. But no, that's a very interesting question. We've seen these scenarios before, certainly, where you do get a decent amount of lightning. But as far as I know, with this particular case, we actually did not get enough charge separation for lightning.
And then when those convective elements did develop, right about this time frame, did snow rates enhance quite a bit?
They did, yeah. I mean, and, sometimes it's hard in northwest Oklahoma to get timely reports, but we were in contact with, our co-op observers up there. I think Forrest was kind of calling around to them, getting some information, and we've made some calls up there to kind of get as much information as we could. And from what we were hearing from the emergency managers and dispatch and whatnot, the calls we did make, that really the rates picked up quite a bit. And this is where we're starting to get, we were piling on top of, we were pushing 6-7 inches or so. And I think shortly after this, we picked up some 10, 12-inch reports from Harper County and Ellis County. So it's pretty impressive, and it seemed to correlate really well with those enhancements in IR satellite there. But
Yeah,
what we
okay,
did is
great.
we tried to sort of explain that in NWS chat, to put a good amount of science as a foundation, but also practical information too. And I think our office is exceptionally good at that. I know most offices are. We really embrace NWS chat as a critical tool for communicating this type of information. But we've really been trying to put emphasis on that, and I feel like we do a really good job. But then, this is an example of how we're saying that these mesoscale bands, that they may not be all that apparent on radar. So for our broadcast meteorologists that may not have had enough time to do a lot of in-depth analysis, certainly they could kind of dive in there and see only a limited amount on radar, but the satellite was what was really helping us see those spikes. So we tried to communicate that. And just a little bit more on the meteorology, just using SBC's Meso-analysis, just grabbed a few of those graphics. You can see that there was quite a bit of moisture within that critical dendritic layer, that -12 to -17C layer, and omega and ascent that was going along with that too. But what time you see later in the day, that starts to kind of shift up to the north and elongate along the border with Oklahoma and Kansas there. So we knew that change would happen, and we wanted to try to communicate that the best way we could. There's a cross section of it. You can see in the pink contours there, that's where the frontogenesis was maximized. We know that's a critical thing that we want to see from a meteorological analysis standpoint, is to see where that area of frontogenesis sets up. And the high-res guidance did exceptionally well with this. They really pinpointed some pretty high amounts. Now, spatially, they may have been a little bit off, and we can refine that with observational data, and we did that. But in general, this was a success for the models. They did pretty well with this. We were just able to, again, take that the extra mile by being able to provide this perspective or this level of detail in the way we communicated through NWS chat. So in this case, we said, hey, there's strong frontogenesis there, and it may sort of shift a little bit to the northwest with time. And then eventually the model sort of indicated that we would have more of an east to west zone that we'd have to watch pretty carefully later in the day. So that's just trying to take all the scientific information. It doesn't mean anything if we can't communicate it practically. So we certainly tried to do that the best we could. And, there were some other aspects of it too. Maybe it's not the most effective way to look at instability, to look at it from an upright standpoint, but there was a little bit of upright instability there too. And certainly I'm sure there was some conditional symmetric instability that was involved with that too, that helps sort of drive those convective elements. But as the day wore on, we saw some sign that this would probably continue a little bit further east. And so there were a few other things we looked at. Kind of jumping back a little bit before the sun rose, we can see that nighttime microphysics. I'll just go through this pretty quickly. If Chad or anybody else has anything, or anybody wants to ask any questions at the end about that, we can certainly pull this imagery back up and look a little more closer at it. But I've personally found these RGBs to be a great way to enhance just some of our traditional analysis through IR and visible, but to really make things pop out pretty well. Here's the traditional visible satellite. I think the experienced forecasters are very used to looking for things like texture. I know some people have described the sort of this increase in texture that you see in visible satellite as sort of a cue towards an increase in convection. You can certainly see that over northwest Oklahoma, but the detail that you see when you skip forward to these RGBs is pretty incredible, really. You can see more than just the texture. You start to be able to separate out and with confidence be able to say, okay, we've got deeper convection going on. We've got some higher cloud elements in there, and it just makes the full picture a lot more, there's a lot more that you can get out of it. Now, me personally, I still feel like I'm not anywhere close to being an expert in analysis of RGB, so we continue to rely on people like Chad that have a lot of experience in that, and the satellite folks. It's always good to hear some of the information that Bill Line puts out, excellent blog posts that he puts out, and it really kind of helps us in operations understand how to interpret this information very well. So this is just one example of how you can really see the convective element start to blossom there in the Watauga area, a little closer to the west side of the Oklahoma City metro, that start to rotate back up into that area that had already seen the heavy snowfall by the time we get to early afternoon. So pretty cool stuff to see there. And we tried to communicate that, obviously saying the cloud tops were cooling in IR satellite, and that within the warm conveyor belt, we'd probably see the higher rates, precipitation rates across north central Oklahoma. But then the question would be, what was our thermal profile like? And so that's another aspect of this multifaceted situation where we're trying to look at the trends in the convection, the precipitation rates, and also the moisture aspect, or the thermal aspects of it, and actually where that transition would be. And so this is a kind of a loop here of the mesonet. And we're fortunate here in Oklahoma to have an excellent observational data here at the surface to be able to kind of monitor this. But the wet bulb temperatures in this case would prove to be very, very important. You see towards the very end of this event, once we got into the late afternoon and evening time frame, the temperatures warmed pretty substantially. So it's kind of a race between, yeah, we're increasing these precipitation rates across northern Oklahoma pretty fast, but at the same time, we're getting more warm, moist advection, and we're starting to push our thermal profiles into an area where we're very comfortable to say is not going to be a snowfall scenario. We're not going to really have the heavy snowfall rates. Instead, we're going to be dealing with just heavier rainfall rates there. So it's just nice to have that confidence from the Mesonet to be able to say that. Now, from a radar perspective, you see in this image, this loop to the left there, really high reflectivity. We're pushing 55 dBz in there, pretty impressive there. And the correlation coefficient shows that we're probably really, really close to being able to get the snow to the ground, but just not quite there yet. We're seeing that melting going on, driving those higher reflectivity rates. But yeah, we're still continuing to pump out information to our core partners to provide that deep analysis that we know our TV folks really need, and the emergency managers that are adept in understanding the meteorology or that are just looking for the practical information. We're trying to provide all that we possibly can to them through NWS chat. And then you can see we also try to highlight that from the radar perspective too, saying you'll see these 50 to 55 dBz areas, and here's what this means. Here's the practical meaning for this. At 2,000 feet, roughly, that's where the snow levels are, and they're close to the ground, but we're not really seeing a whole lot of snow in Alfalfa County around the Cherokee area and the advanced radar. That's just basically just what we're seeing on radar is just sort of that melting layer that's getting pretty close to the ground there. So it's just kind of a matter of trying to put all that information we possibly can out there. Now, another way that we've found a lot of success with, and sometimes this really helps in the rural areas. I know Cindy Elsenheimer and I, we found this when we both worked in Amarillo. We really used this quite a bit, and I think we presented at AMS on that, talking about how valuable this sort of mining this information from Google traffic can be. And you see the trends throughout the day here, just of the traffic that's pretty slow in the areas where the heavier snowfall rates are. So in the absence of reports, if we're struggling to get reports, sometimes it really helps just to see the patterns of the traffic, along 412, which is a pretty heavily traveled route. And it's enough to where that Google is able to get the data to show that it's pretty slow in this scenario here. And we can see the extent of that a little bit, the spatial extent and the temporal changes with that. So it's a way for us to really understand those impacts of the heavier snowfall rates. So if you haven't had a chance to use this in your office, certainly it's a great tool to be able to do that. All right, so one last slide here just to kind of tie some of this up. I know we went through it kind of fast, but I just want to emphasize this transferring science into messaging. Again, we can do all the science we want to, all the great work the researchers and modelers have done, but if we can't translate that into something that's useful for our partners and the public, then it's really all for nothing. So we try to do everything we can to sort of highlight that and say, hey, in this case, it looks like, that the thermal profiles are such that we'll probably be very, very close to the transition, but at least we can say one thing for sure. In this case, we can say, hey, we're not going to see a lot of ice with this. It should be a clean transition from rain to snow, or as we warm up from snow to rain, without a lot of ice concerns in between. Probably not even a lot of chance for sleet in this case. And that's just based on our analysis of the thermal profiles and the models and being able to kind of provide that level of detail. But, just also practical things too, like saying, okay, over the next hour, snow rates may pick up considerably based on trends. So just at that level of information, we try to be as intentional as we can with that. And then when we can, we try to summarize all this into the Mesoscale updates that go out through the AFD product for the folks that may not be in chat that also want to have this information. So that's been a kind of a thing we've done here in the Norman office too. But again, this is just our perspective, of how valuable that mesoscale analysis is. It's something that I think is really important to the end user, and it's not just for convection. It's not just for severe thunderstorms. There's more to it than that. Obviously, it can be used in fire weather. Todd and I at the office have had some pretty good conversations about that, and it can be used in winter weather. So, and here's just a few quick bullet points just for discussion's sake that I put up there just to sort of wrap some of this up and some of our takeaways from this event. And feel free to read through those or any questions or comments. I'm kind of looking forward to this discussion here. So I'll go ahead and turn it back to Chad, I believe.
Yeah. So yeah, thanks, Randy. So I want you to go back to a particular slide. Go back to that one IR loop that I was asking questions on earlier. And while you do that, just briefly, talk about the science that you put in the NWS chat, because there's a wide range of users in there. So you can think of it as it's from broadcast mets who have degrees in meteorology, all the way to maybe a rural emergency manager that maybe weather savvy, but just doesn't have, that background. But you're adding quite a bit of meteorology and science into these NWS chats. Can you just talk about that and maybe any of the feedback you've gotten? Is it too much or too little?
Yeah, absolutely, Chad. We've asked for feedback, and we've gotten feedback even when we haven't asked for it. But we've had these conversations in operations too, and working with Rick, our WCM, and trying to find the best balance of science and practical information too. And I think we've settled on this idea that as long as we've got a good balance of it, as long as we're putting a good amount of science in there, that's really appreciated from some of the high-end users. And so the average user in NWS chat may not understand it to a full extent, but they know how to filter that out and look for the more practical information. So I think we've all been very good at understanding that we can be concise with the science information that really helps our TV partners, but yet we can also and sort of fill the gaps in with practically what that means to your average, say, emergency manager that may not have a meteorology background. And the feedback we've gotten is we can't possibly put enough information in the NWS chat. We've heard that from our broadcast partners. Our emergency managers have said similar, is the more the better. The more that we can take all this meteorological information and put it into relevant terms that explain what's going on, the more that it's not too much. Because we've asked them that in our media workshops. We said, is this too much? Are we chatting too much and cluttering up the screen? Mm-hmm. And they've all unanimously said absolutely not. And so I think that's been, for us, that's where we've really kind of pushed forward and made sure that we try to be as active as we can in NWS chat to fill that need, because there's clearly a need out there.
Yeah, that's great. Okay, 2 more questions before I pass it back over to Brian Gockel. Number 1 relates to this image. So you can obviously see a trowel is in place and you have a cyclone with a warm conveyor belt over eastern Oklahoma. But talk about this, that developing almost like convection to the west that's basically being transported right into the trowel. I mean, is that an important feature to track? When you saw that convection, we can call it convection, or at least much cooler cloud tops, did it give you confidence that there would be heavy snow rates? Did it give you confidence that would enhance the trowel? Can you talk a little bit about that?
Yeah, I think so, Chad. I think the first reaction we had to it was basically just, well, we know this is going to drive the heavier rates for sure. And even before it kind of got all wrapped back up in the trowel and kind of the mature aspects of how that would evolve with time, that's certainly a good point, because that has implications for maybe how things evolve and maybe going into the afternoon hours. But I think our first, at least knee-jerk reaction to that was, there's no way we can have these enhancements in the cloud top, without having some pretty decent rates go along with it. We had the thermal profiles. We already had a decent amount of snow without the convective elements. So certainly once we see these convective elements in there, knowing the background information we have with the frontogenesis before the trowel even started to kind of move a little bit further east, that we would kind of be in trouble in that area, and we'd probably really pile on them out. So I think what you said really hit on it by you saying that it really added confidence, because some of the mesoscale guidance was a little bit in conflict. There were some lower amounts, there were some higher amounts, but I think some of the higher end amounts that the HREF was giving, we were able to say, okay, this is why. Here's the physical reason why it's given those higher amounts. And so yes, it did. I think it increased our confidence quite a bit.
Well, that's the thing, because obviously the event has started right before you see these cooler cloud tops elements. You already have the forecast out. That's pretty robust. I mean, 12 to 14 inch, snowfall forecast. There's probably a little uncertainty, right? Like, you're still like, winter weather is so finicky that, like, when you saw these cooler cloud tops, there was probably almost like a sigh of relief. Okay, the forecast is probably representative based on this. It's not only that, to be able to look at this in the satellite imagery for the forecaster, but also then being able to message that, we're seeing this, and then we have, which allows us to have more confidence in the forecast. So
Yeah, absolutely, Chad.
Yeah.
I was just going to add just a little bit to that. The thermal profile aspect of it too is important, because that was one of the most uncertain aspects of this event, was were we going to be able to wet bulb down enough to the thermal profile to get, and obviously with the heavier rates we're going to be able to do that, certainly. So we were on the fence with the thermal profile too. So yeah, the rates were there, so we knew if we got the rates we would not be in a bad situation as far as the thermal profile. So those temperatures, even though they were hovering around 32, the surface temperature, that was enough. So I think that really helped too.
What about, I noticed that you're using CONUS imagery here. What about, was there any indication that you would call a mesoscale sector over this area? If there was, because I don't remember if there was, did you utilize that data? What is, talk about the importance, or maybe it's not important, of the 1 minute imagery with these winter weather events.
Yeah, I mean, I think it's one of those things where the more data we can get, the better. Maybe we can certainly pull something out of there. I think it's maybe less useful in the winter weather events than, say, the convective events. You know, we've kind of found some use with filling in the gaps for the radar. The radar volume scan time takes 5 or 6 minutes looking for hailstorms, for example, to be able to see those spikes in the overshooting top. The 1 minute imagery is just really, really helpful with that. In winter weather, it's not quite as rapidly evolving, so it's one of those things to where I'm not sure that it would be as much value. If we had it and we had access to it, which I honestly, Chad, cannot remember if we had a mesoscale sector for this particular case or not. We ended up just, with the limitations of some telework involved in this, we ended up kind of just mainly using the CONUS imagery. But if we had it, I think we could probably find some value, and I just don't think it's quite as valuable, say, it would be in a convective environment. I'd be curious on your perspective of that, though.
Yeah, no, I think I would probably lean towards what you're saying as well. But you know, I think your perspective is important on that. And you know, and that's one of the reasons why winter weather is just ranked a bit lower, you know, on the mesoscale domain request priorities, right? It's like in the 13, 14 range. And even like a slight marginal risk is higher than that. So but it's good to always ask that and make sure that, you know, you're seeing the same things. You know, so with that, you know, let me thank Randy, and then thank you for allowing me to facilitate and ask some questions. Brian, I'll pass it over to you to thank everyone for coming.
Hey, sounds great, Chad. Thanks for facilitating. I really appreciate that. We will be glad. In fact, we want to get to some more Q&A and some extended discussion. So hang on if you can. We understand some folks have conflicting meetings now, but for those who can, definitely encouraged to hang on, and we're going to get to those questions in chat. Feel free to add some more there. Hey, and here's the reminder on the screen. We've got another meeting scheduled, another Satellite Book Club meeting scheduled next week. Pam Sullivan's coming back, System Program Director for GOES-R, becoming GeoXO program now, for a presentation on the satellite constellations that are being considered for and proposed for GeoXO. They've got big plans with building to the current system GOES baseline to include additional functionality. That's what's being proposed, and they want to share these recommendations with you. And as the program proceeds, the program is going to need NWS support, so we want to be fully on board with it. So come back if you can for that, in particular if you missed her Pam's last update, I think early in the fall. So there's also a survey I want to mention in the link that Lee put in there. So before you go, your feedback is more than welcome in the survey. The link is there as well. Lee Kashad, the team, TerraS team, has up the links for how to reach out to us for either satellite configurations for your AWIPS, or to touch base with us for scheduling a future Satellite Book Club meeting. If you have a topic you'd like to present, we'd love to have you. Please contact Kashad. And reminder that there's the NWS chat room, TerraS. So we want to get back to the questions now. I think Chad asked the one about the mesos, Bill Lyons' question related to winter weather events. So let's go to Joe's Joe had a question, Randy. If you could discuss for a moment your who your end users are at the Norman office, in particular when it comes to snow events, and how their needs drive aspects of your forecast process.
Yeah, no, that's excellent. I mean, I think it's very important, obviously, to know who your end user is. And, you know, in this case, I think the Department of Transportation, I know Bruce in our office has worked really hard to try to get even more in contact with them to understand their needs quite a bit. So we continue to work through that. And I believe they're in NWS chat. And so, but a lot of it ends up being our broadcast partners too, just to sort of help them with the analysis aspect of it. You know, they do really good. They're excellent meteorologists. We have a great TV meteorologist in our area, in our market, with 3 different markets that sort of are in our area too. But it really helps them to sort of to have our analysis as a foundation for what they're doing as well. But then a lot of our emergency managers end up being really adept at meteorology too, so they understand some of the deeper meteorology as well, and they really appreciate us being able to provide that level of detail to them. So it's a pretty wide spectrum what we have in our area. But snow in Oklahoma can be very impactful. Obviously, it's, you know, we don't have quite the climatology for snow that say maybe Iowa or Wisconsin does, but when it happens here, usually it's a messy transition and ice involved and that sort of thing. So there's a lot of interest from a wide range of our partners in government and our partners in broadcast, obviously, to try to provide the best information we can.
All right, thanks for that. We've got a comment from Jim Ledoux about a winter weather lesson with Meso-analyst considerations for winter, and Randy's co-author on that. Does everyone know where to find that? Is there maybe we can post a link somewhere for that, or some reference in the chat or notes if anyone has an answer for that. I'm not sure exactly where that is. The winter weather lesson that Jim is referring to. While that is done, another question from Steve Cobb about the use of cams during convective season with longer lead time area favoring supercells. Do you think cams may be equally useful in winter weather with so many factors at play, thermal profile, wet bulb profiles, and so on? And I can say, if he's talking about, Steve, if you're asking about traffic cams, I know that's a big factor even in the east, where we have some terrain, and the precip type changeover can occur rapidly at higher elevations well before it settles down into the valleys, but also could be useful for tracking rain snow line. Randy, any comments on that use of cams?
Yeah, sure. I think it's pretty important. It really is. It seems like the HREF was very helpful in this case. And what's really good about the HREF is you get a mean product. So basically you can have an average of all the ensemble members, but then also the maximum too. And in this case, I believe our amounts kind of pushed the maximum end. And I think that was just a function of some uncertainties with the thermal profile and exactly how things would come together, which, you know, so then you got a little bit of a spectrum from the cams and from the high res guidance of what may happen, and you have to sort of work that out. And so you can say that on the upper end that we may have some localized areas that could push a foot of snow accumulation, but you really don't have the confidence in that until you see things come together. And both the Mesonet and the satellite observations kind of really helped us say, okay, now the higher end of this high res guidance certainly is something that we're concerned about that may actually play out. But yeah, absolutely, Steve. I think that's definitely an area that with time, I think the cams continue to get better, and that's going to provide even more solid guidance for us. And as far as the traffic cameras, I think that was a part of this too, is we would use those, the ODOT cameras, to kind of look and see where those transitions were. As soon as we'd start to see white on the ground, we knew that we were picking up accumulation in those areas. So it's a really useful tool too.
Okay, I had a question on the dry conveyor belt. I'm sorry if I missed this, Randy. Is that a general synoptic scale feature, or is that accentuated by the topography off to your west, the Southern Rockies there, or maybe sometimes a combination of both?
Yeah, I think probably a combination of both. It's certainly something even further east. I'm sure that the offices further east deal with quite a bit, but it seems to be accentuated by the Rockies. And obviously, you have the ascent or the descent that occurs within that airstream, and then obviously with the terrain enhancements of that too. I'm sure that plays a role in it too. But yeah, sometimes if you just have small errors in the exact position of how things play out with the position of the mid-latitude cyclone, then that dry slot ends up shifting just a little bit. So being able to track that in water vapor imagery, especially the 7.3 micron imagery, really helps to be able to find where that delineation is between the deeper saturation and where we may lose the potential for ice and end up in sometimes even a freezing drizzle scenario. We've seen this before, to where we get enough saturation down low and we're cold enough to where we lose the ice aloft, so we don't have the dendrites, and we go from snow into having more of a freezing drizzle scenario, which can be more impactful than snow sometimes. So being able to track that and know when that's going to happen is very important.
Okay, thank you. And let's see, Brian Mata has a question. Is it useful to use all 3 water vapor channels instead of just one?
Yeah, I think so. Before, we had the mid-level water vapor, and then now we've got all 3, and that's really helped. So I think for things like tracking, even in springtime, for seeing the details within the elevated mix layer and the capping inversion that sort of results from that's very important. But like you just said, in the wintertime with tracking the dry slot, you can't beat the 7.3 for that. But then, kind of like this example we showed earlier too, the high-level water vapor can be very effective for sort of seeing some of those model errors, or being able to sort of kind of get a little bit idea of the overall structure of the synoptic system as well. So in this case, I think we found use for all 3 water vapor imagery, different bands, all 3 different bands.
Mm-hmm. And speaking of model guidance, you mentioned it a few times as well. You mentioned the importance of the profiles, understanding what the profile is for precip type determination. You mentioned model soundings. Have you yet consulted the GOES soundings or the NewCap soundings for that? Apologies if you mentioned that, I missed it.
Yeah, we've gotten some use out of them, especially, it just depends on the scenario. It seems like, it seems like depending on how much depth of moisture, or, various aspects of what we're looking for in the sounding, they can be very useful, I think. There's other times where it seems like just more of an observational base, looking at the actual, the model soundings, or certainly the observational soundings that we launch, can be helpful, especially near the ground, where sometimes satellite may struggle a little bit more with that. The boundary layer conditions and convective situations, it seems like that we'll get a little more detail from that. And then, but yeah, we try to integrate the NewCaps when we can to sort of supplement that, especially spatially, since obviously we don't have a sounding as nearly as at the spatial resolution that we would like to have an actual observed sounding, and that can kind of supplement it some.
Okay, I think that's all the questions we have in chat. I hope I didn't miss any. Are there any other last call? We have thanks from Dan, and any other questions for Randy before we wrap it up? Okay then, well, listen, we wanted to thank you again. Thank Randy for putting together this presentation and bringing it to us. It's nice to see winter weather. If you can't have it, at least enjoy others who have the drama of having to forecast in it. Again, there's a survey in the chat link that Lee left there. We encourage your feedback, and want to give another plug for next week's GeoXO brief by the System Program Director, Pam Sullivan. Look forward to seeing you all next Thursday, the 14th, and thank you again for your participation.
Thanks, Brian.
So long all.